So we want to look at L terminal, F terminal to see if it's talking. We go out to the alternator, we put a pin back probing into the connector on the L terminal and put a pin on the F connector. Take your DVOM and you turn it to frequency. We put our red lead on the pin on the L terminal and our black lead to ground. We should see 128 plus or minus 10 as far as the frequency. Again, have 10 seconds after you start the vehicle. But now we want to take that clip, you move it over to the F terminal, you should see 400 hertz plus or minus 10. That way you know it's communicating. But look at this lab scope. Did anybody here use lab scopes? Okay, if you don't use lab scopes, they're a fancy voltmeter. You just got voltage over time. And if you'll notice the time on this one, I set that at 5 milliseconds, which is 5 thousandths of a second. The reason I did that is so I could capture how wide each one of those on times were, that pulse width that's up here. Figure out how wide that is. The other thing is, you see the 2.5 volts? Each square I set at 2.5 volts. That's why that R is your reference line, because here's 0, and here's 5 volts. Excuse me, here's 2.5 volts, and that makes 5 volts, because it goes up 2.5 volts each square. Goes up 2 squares, that's where you get your 5 volts. Because a lot of times when people see a 5 volt reference at a variable duty cycle, they assume they're going to see 5 volts there. And the key to this is you have to take that 5 volts times the duty cycle percentage to get the true voltage if you're going to try to test it with voltage. But on a lab scope, you can see it right away. It goes straight up to 5 volts. And that's about a 70% pulse width right there. Now, on this one, I slowed it down to 2 milliseconds. And the reason I slowed it down is because this one's 400 times a second, so that I could capture it a little bit better. And if you'll notice, it's still set at 2.5 volts. So you go up to, there's 5, there's 10, and then there's 12, and then 12.5 at the very top. But that's one way to see if it's communicating back if you're using a lab scope. So here's how it all works. You turn the key on. That BCM looks at the state of charge of the battery through those voltage sense lines. It looks at the current flow from that battery current sensor. It takes the intake air temperature sensor and it calculates it on a chart to see, based on the battery temperature, the voltage, and the amperage or current flow, what should I set the voltage set point at? So it does its calculation and sends that calculation up to the PCM. Now, at this point in time, let's just say it says, okay, give me 14.5 volts. So it tells the PCM that it wants 14.5 volts. So the PCM then sends that 14.5 volt signal over there on a variable duty cycle, which I believe, if you look at your book, like page 8, is about 72% or something like that. So the 72% goes over there, 128 hertz. And now the vehicle starts up, the alternator starts to turn. It's communicating back on the F terminal at 400 times a second that it's doing 14.5 volts. The PCM sees this and is good with it. But then you think to yourself, what if I've got a voltage drop in that line? Meaning that even though the alternator is putting out 14.5 volts, what's actually making it to the battery? So the BCM double checks to make sure that that 14.5 made it down to the battery. It looks at those voltage sense lines and says, oh my gosh, only 14 volts made it down here. So I've got to do some adjustments. It then updates the voltage set point signal and says, give me 15 volts. Now it knows 14.5 is going to make it to the battery. But at the same time, if that voltage drop is high, it's going to set a code and tell you that you've got a voltage problem. Okay, so let's talk about the truck line. The truck line is a little bit different, and it's called standalone regulated voltage control. Just like your computer at home, if you're no longer on the network, you're working on your computer by itself, it's standalone. So here's one of the main differences here. When you look at the battery current sensor on the older ones, on the RVC ones we just talked about, the truck line has a battery control module. Sounds expensive, doesn't it? Because basically that thing is a BCM. It's a battery control module. It has a thermistor built inside of it, which a thermal resistor is a resistor that reacts to heat. And so it uses that, which is a thermistor, to determine the temperature. It also looks at the battery current because it has voltage sense lines that are plugged into it. It looks at the amperage through that amp clamp that's built into it. And then it makes the determination what the voltage set point should be. This is how it works. When you turn on the key, it looks at the current flow. This battery control module looks at the current flow. It looks at the voltage. It looks at the temperature, determines what the voltage set point should be, and communicates that to the alternator's microprocessor through the same means, 128 hertz signal. Starts charging, and it communicates back on the F terminal. But at the same time, the PCM and the BCM are connected to this battery control module through a Class 2 serial data port so that it can communicate vehicle conditions, vehicle speed sensor, throttle position sensor, so on and so forth. The beautiful thing about this, you don't have to dig through that massive wires at the PCM to find the L and the F if you're doing some wiring diagnostics. See the difference here? You've got the L terminal that goes straight over to the alternator right there. So you can check it at the alternator and check it here to see where the disconnect is if you have an issue. Your F terminal is right here, going from the alternator to here. You got your ignition wires and your ground, so it can determine the state of charge of the battery. And then it's got that Class 2 serial data port there. Where do they mount these? Have you seen any of these on the trucks? Sitting right over there by the battery on the battery cable? They put it close to the battery as they possibly can. So the key to that is if you get a code on that one, again, unplug it, clean it off, put some dielectric grease, see if it goes away. Because about 80% of the time, 80-85% of the time, that's where the problem is in the plug-in that we find on the technical support line. So it still has the same connector. It still has the same connector. It's the same alternator regulator as the other one. No difference. It's just being told what to do by somebody else. Same alternator, same regulator. Here's some of our modes of operation. Talk about these. And some of these are very important to diagnostics too. Startup mode, we've got charge mode, and the gauge isn't going to flip around like that. I mean, it could be at any of those positions, but it's just going to depend on what mode it's in. And as far as knowing what mode it is or recognizing that as a diagnostic tool, it's not really as important as you would think. It's just that you want to explain why it does what it does. Fuel economy mode, voltage reduction mode, sulfation prevention mode, headlamp mode, fuel pump boost mode, de-ice mode, and windshield wiper mode. And several of these are the same thing when you look at them. And I understand they're differentiated because if you turn your windshield wipers on instead of your headlights, they call it a different mode, but it's still the same thing. And let me explain. Startup mode, remember we start the car and it waits 10 seconds to kick on, but when it does, it immediately goes to 14.3 volts to recharge any battery amperage that needs to be placed back into the battery that we used upon startup. 14.3 volts, when you look at your chart, 14.3 volts, when you look at your chart, is 70% duty cycle. 70% duty cycle. So if that's a 5-volt reference, and it's 70% duty cycle, I should see 3.5 volts on that line 10 seconds after I start the vehicle. Or if you do it the easy way, turn your DVOM to duty cycle, it'll match what your scan tool says. But I'll show you that in a second. Charge mode is where everything is on. It's just time for this thing to charge. It goes between 13.9 and 15.5, just like the older units used to do. Now 15.5 seems a little high, doesn't it? But that's completely normal for this system. You just don't want to be there for a long, long time because then you got something else going on. The reason I say that is Ford goes up to 16 volts. If you saw 16 volts on a car in the past, what would you assume? Yeah, you're overcharging. You got a bad alternator or something. Here's a story for you. They got the guy who works out in the DC. He comes to me and says, "Hey, look, I've got something going on with my truck. It's a diesel truck. He had his battery tested. I went through the whole question and answer session with him, and yes, he had his batteries tested, all this stuff." He brings it up there. I plug the scan tool in. It's doing 97% duty cycle on the charging system PID, which is parameter identification. 97% duty cycle. Look up the chart, 97% is 16 volts. It's doing exactly what it's asked to do. I go out there, first thing I do is unplug the two batteries, check them both. One of them has a dead set one in it. Because they try to check them both together. And I think that's where they failed. But the reason I bring that up is because, yes, 16 volts can happen on the Fords, or 15.5 can happen on this. But it shouldn't stay there. If it does, something else is pulling too much current, or you've got a sufficient amount of voltage drop or corrosion in the lines. So charge mode, fuel economy mode is the opposite. This is where you're tooling down the highway, the air conditioner's off, the window's down, there's just no power needed. Battery's at full state of charge, boom, shuts it down to 12.4 to 13.1. Shuts the voltage down. A lot of people think it turns it off. It doesn't, it just reduces the voltage. Voltage reduction mode is somewhere in the middle, where it's not quite enough to drop it all the way down, so it's around 12.9, up to 12.9. Because remember, this thing can do 70 millivolts a step to turn the thing up and down. Sulfation prevention mode. The computer identifies that this alternator has not, or the actual system hadn't come off of 13.2 volts for a period of 45 minutes over the cycles. Doesn't mean you got to drive it for 45 minutes. It just means in the 45-minute period between turn on and turn off, it's noticed that it hadn't gotten off of 13.2. It automatically assumes that the sulfuric acid is stuck in the plates and tries to blast it out by going to 13.9 to 15.5 back and forth till in between that range, hoping to knock it off of there. If it doesn't, then you'll get a code and the battery light will come on. Because if that thing's sulfated, it's not any good. Headlight mode is perfect for you guys because when your customer calls, remember earlier I talked about the customer that got the new alternator, had the car since it was new, never saw a problem with it, and now the voltage is dropping off, now that they're actually looking at the voltmeter. Tell them to turn the lights on. That voltage will gradually pull back up. If they're in fuel economy mode going down the highway, it's at 12.4, turn the headlights on, goes back up to 14.5 volts. Fuel pump boost mode, here's where the throttle position sensor comes into play. If you're in economy mode and you push that fuel pedal down past 90% wide open throttle, which is on your throttle position sensor, it will kick the voltage back up to 13.4 volts to overcome the fuel pump and the ignition system so that the car will run correctly. De-ice mode is exactly the same as charging mode because at this point in time you have a ton of stuff going on, right? You've got your blower motor going, you got your AC compressor, you got your condenser fan motor going, and in most cases you have that giant short in the back window that they call a de-icer. So it takes a lot of current to run all that stuff. It kicks it back up to 13.9 to 15.5 to make sure there's ample power to run all that stuff. Windshield wiper mode, same thing as headlight mode, 14.5. And one reason they do that for headlight mode and windshield wiper mode is even though you have wattage available, if you have a lower voltage, lights will be affected by bright and dimness when you turn the voltage up and down, because when the pressure goes up and down, the lights do too. And the same thing applies with the windshield wipers. They will go a little bit slower if it drops down. So it's good just to keep it at a constant voltage.